Okay, let's begin. Well, welcome to the Survey virtual graduate course on Phobos and Deimos, the moons of Mars. We're very pleased to have a presentation today by Sasha Basilevsky. My name is Carly Peters, and I will be moderating today's session. Here's a few ground rules for those of you who haven't been with us in previous sessions. The audio will be limited just to the speaker as well as the moderator, myself. However, we do encourage everyone who is participating to be thinking of comments or questions and to type them into the chat box there on the lower left part of your Connect session. Comments and questions will be addressed during the question and answer period, so we'll accumulate them, but as they occur to you, feel free to include them into the chat box. Notice in green the website there. On the website you will find the lecture readings, key questions identified by the lecture slides, videos, and a recording of the session after the session is complete. So please use this resource for a lot of background material and material that's ongoing. The course is sponsored by the Solar System Exploration Virtual Research Institute, otherwise known as SURVEY. The Institute has a number of teams across the country, and many of them, perhaps most of them, are engaged in Phobos-Deimos systems exploration research. This particular course is co-sponsored by two teams, Brown University's survey team, Evolution and Environment of Exploration Destinations, otherwise known as SEED, of which I am the PI, and also by University of Central Florida's Center for Lunar and Asteroid Surface Science, otherwise known as CLASS, and Dan Britt is the PI there. The course began on September 14th, and today we're into our sixth lecture of very informative lectures and discussion sessions. The full schedule can be found on the site itself. Today's charts, as well as the reading list topics for today, can be found on the website as well. Today's lecture will focus on the geology and geomorphology of Phobos and Deimos. The presentation is by Alexander Basilevsky of the Vernadsky Institute in Moscow. Now, unfortunately, Sasha himself cannot be present for the presentation. So he has arranged for our colleague, Ken Ramsley, to show and discuss his presentation. Let me tell you a little bit about Sasha. Dr. Alexander Basilevsky is a senior scientist and chief of the Laboratory of Comparative Planetology of the Vernadsky Institute of Geochemistry and Analytical Chemistry of the Russian Academy of Sciences. And he's held that position since 1975. He's also a visiting professor at Brown University from 1994 to the present. Dr. Basilevsky received his PhD in 1968 in geochemistry and his SCD in geochemistry and planetary science from the Vernadsky Institute. He received his professorship in geochemistry in 2007 from the Vernadsky Institute. Now, in addition to numerous guest teaching appointments, Dr. Basilevsky has conducted research as a guest scientist at the Department of Astronomy, Oulu University, the Max Planck Institute of Solar System Research, the Freie University of Berlin. Dr. Basilevsky is currently supporting the Lunar Globe resource missions in the areas of landing site selection and characterization and preparation for in situ study programs. His space mission involvement and support has also included preparations for the Phobos Grunt missions run by Russia, Mars Express by ESA, Mars Odyssey, Magellan, Voyager, Neptune, Encounter of the U.S. Venera and Vega missions to Venus, he was deeply involved in, as well as the Lunokhod 1, 2, and Luna 16, 20, and 24 missions to the Moon by USSR. Dr. Basilevsky is the author of several studies on the nature of Phobos geology and the survival time of boulders on airless bodies. So with no further ado, let me turn this over to Ken Ramsey, who is presenting Sasha's slide and will speak to us on the topic of geology and geomorphology of Phobos and Deimos.
Thanks, Carly. I can't show you our tripod, but in the spirit of geology, I just want everybody to know that it is a 2-liter beer stein turned upside down with a webcam attached to the top of it. It makes it very easy for panning and adjusting and so forth, and it's very consistent with the topic of geological exploration, which seems to combine beer and rocks very intimately. The goal of today's lecture, really, and this is Sasha trying to get a handle on the Phobos as sort of not so much a unit, but a big picture of Phobos. We've explored a lot of aspects of Phobos so far. We've poked at the dynamics of the system. In later classes, we're going to continue to look at the dynamics of the Phobos system and some mineralogy and space weathering and so forth. But so today's class is really the best last chance we're going to have to see Phobos as a complete system. So, of course, when you're trying to describe a complete system, you end up looking at different pieces of it. But the spirit of today's lecture and today's message from Sasha is we want to look at all of the aspects of Phobos and try to relate them together, get a sense of, a geologist's sense of what Phobos is like, and what it would be like to investigate it. What are the things that are driving our interest in studying Phobos? This is very much a geological topic. We won't be looking at mineralogy. We won't be looking at a lot about dynamics. This is going to be definitely closer to rocks and craters and the sorts of things that got a lot of people interested in geology to begin with. Okay, so as an overview, we're going to look at craters. We're going to look at regolith and including boulders. A lot about boulders. Sasha and his team have been studying the fate of boulders on airless bodies, and that includes Phobos. We'll have another look at grooves from Sasha's perspective and help us to get a better sense of perhaps what the grooves might be about and more descriptive information about that. And we'll touch on Deimos near the end. We don't know as much about Deimos, but we will present what we do know as far as what we've collected to this point. This presentation, these slides that Sasha has produced for us, and I have adjusted them a little bit just so that it makes it a little bit easier for me to present. It's based on a paper that was published last year. The overall sense of the geology and geomorphology of Phobos. I'm a co-author on that paper. That's what happens when you run into colleagues. They ask you, do you know anything about the orbital, the fate of Phobos with respect to impacts and the flux and velocities and so forth? And I said, yeah, I think I can help you out with that. And so that's what I was spending a fair portion of my last summer investigating. And as part of that, came up to speed on this whole process that Sasha is presenting here. So I'm not just a presenter. I am fairly well acquainted with the points that Sasha is making, and we'll take it from there. Okay, for those who may not have attended any of these classes yet, this is just a little bit of history. I know Dan Britt gave us a very thorough history of the discovery of Phobos and so forth, but just to touch on this again, Phobos was hypothesized, Phobos and Deimos, or these two moons of Mars, were hypothesized to be there, just sort of on a, well, the Earth has one moon, Jupiter has 4 moons, so Mars should have 2 moons. That's sort of the logic of the classical world, and not particularly for that reason alone. Asaph Hall, working with, at the time, perhaps, I believe, the largest telescope in the world, one of the largest telescopes in the world, a giant Clark refractor, the Naval Observatory, went through the effort of trying to discover these things, and it was clear that if they were there at all, they were going to be pretty small, because if they were big like our moon, we would have seen them quite a bit sooner. So Asaph, his wife Angelina Stickney Hall, worked together on this project, and Angelina was critical to this research, did a lot of calculations and support, and without the two working together, this would have taken a lot longer. We see Crater Hall near the south pole of Phobos, and let me practice with this pointer. Okay, here we go. So here's Crater Hall near the South Pole, and then of course Crater Stickney in honor of Angelina Stickney Hall. Okay, so let's have just an overview picture of Phobos. And Phobos, it's one of those weird things you think, well, it's really small, but then it's really not that small. The dimensions, are listed here, 26, 22, 18 kilometers. Okay, well, that's, compared to a lot of things in the solar system, that's pretty small. But if you spread that land area out, it's about half of Long Island. And I really, considering that I'm in Rhode Island, I really hate to use Rhode Island as a unit of measure, but the surface area of Phobos is about 50% bigger than the surface area of Rhode Island. So, and if you've ever taken classes at Brown in geology, we do field trips in Rhode Island, and there's a lot of diversity in Rhode Island. There's a lot of things to investigate. There's a lot of things that we're still learning about Rhode Island, and it's within driving distance, an hour or so. So, I mean, but you could never say that you could figure out the geology of Rhode Island in an afternoon or a week or a month. I mean, even, centuries after Europeans have come to Rhode Island, we're still making discoveries and learning more about Rhode Island. So the idea that we could go to Phobos and learn everything there is about Phobos in a week or 2 weeks or whatever, keep in mind, there could be a lot going on Phobos that's going to take more than just one expedition. Okay, so here's some other odd things about Phobos. Besides the fact that it's small, but it's really big, or bigger than we really think, it orbits around Mars rapidly. If you were to compare the orbits of Phobos and Deimos to the kind of satellites that we have orbiting the Earth, Phobos orbits about where our GPS satellites orbit, at sort of between geosynchronous and low Earth. And it's not a really rapid orbit around Mars. The fastest orbits around Mars would be like once every 2 hours. But it orbits, as Dan pointed out, 3 times a day. And because Mars is rotating, there's sort of an elaborate dance that goes on, because Mars is rotating, Phobos is orbiting. And so you have this really weird thing that happens. Every 11 hours, if you're on Mars, Phobos rises, but it rises in the west. It doesn't rise in the east, it rises in the west. And just sort of like a satellite that you might see going overhead, at night around, in a dark place where you can still see satellites, you'll see it go overhead. And in the case of Phobos, it'll take about 3 hours from the time that it rises to the time that it sets. Now, if you're thinking about using Phobos as a base to observe Mars, you have to understand that it works backwards the same way. If you're on Phobos and you're looking back at Mars at one particular place on Mars, or you're trying to communicate on Mars, you're going to have a 3-hour window every 11 hours. Okay, so where is it exactly? Well, it's about the distance from the center of Mars to Phobos is about 9,400 kilometers. From the surface of Mars, it's about 6,000 kilometers. All right, and I mean, if you're standing on the surface of Mars, it's not a dot. In fact, it's about third the size of our own moon. If we were look at Phobos from Mars or look at our own moon from Earth, it's about 1/3 the size. And so you can imagine it would be comparable to the southern highlands of the moon, or a little bit bigger than Imbrium. So you would look up and you would be able to see that, you know, it's more than just a dot. It has some shape. And as it rises, it comes over in different phases. You'd be able to see more of the leading hemisphere as it comes at you, and then more of the, you know, sub-Mars hemisphere as it's overhead, and then more towards the trailing hemisphere as it disappears. So if you're an observer, an amateur astronomer on the surface of Mars, you'd have a pretty good look at Phobos as it passes overhead in a telescope. As has been mentioned before, it's very dark, and I won't get into that, more than to say that that gives some indication of its origin, perhaps. Fairly low density, which also begs the question: what's it made out of? Is it air? Is it voids? Not airspace, but voids between large chunks, or is there a lot of water inside Phobos? And the escape velocity is this is one of these dynamics things that we'll be talking about, I expect, for probably the rest of the class. But the escape velocity of 11.4 meters per second, that's correct, but probably not in very many places on Phobos. If you're on the north or south pole of Phobos, it's going to be greater. But Phobos is rotating. It's rotating at the same rate that it's orbiting Mars, and so that changes the dynamics of the local gravity. It's also deep in the gravity well of Mars. The gravity distribution of Phobos is a little odd because it's not spherical. So everywhere you are on Phobos, the escape velocity is different. In fact, if you're running to the west versus running to the east, if you assume you can really run on Phobos, even that is different. If you're going to the west, you actually will have to go maybe almost up to 20 meters per second in order to escape. And if you're shooting off from the rim of Stickney Crater at the highest elevation of Phobos, it could be as little as 4 or 5 meters per second in order to reach escape velocity. So the whole idea of escape velocity and how motion interacts with Phobos is very complicated. Okay, there are slides. This slide presentation is already online, and I invite you to download it at your convenience. I understand that this map is not going to be something that you can see readily online here, but just to give you a sense that Phobos has a lot of geological diversity. There are craters that have deeper profiles, deeper depth diameter ratios, which suggests that they're younger, whereas older craters are mapped here in different colors. The shallower craters are in blue. The green is sort of the medium depth diameter, and the tan outlines are the deeper depth diameter. You can also, when you look at this map, you'll see that there are other aspects of the craters that are mapped, whether or not there's been landslides and odd shapes to the craters, and the extent to which they've been modified in various ways. I'll just invite you to have a look at this map at your convenience. Okay, so here's some craters that we see fairly often. They're in the northern hemisphere. They're fairly well imaged. Drunlo and Clustril. They're close to the North Pole, and immediately, of course, this is a very Phobos-looking thing. You've got craters that are streaked with grooves. Let's see. Okay, and all craters. This is something that Nico mentioned during the second class. That all craters on Phobos are simple craters, bowl-shaped craters. And here's a profile that goes through the two craters, Drunlo and Clustril. And you can see by the profile that it's your pretty much standard issue bowl-shaped crater, depth diameter of a fresh kind of crater of about 0.2, 0.25, something like that. Sasha did considerable amount of research on trying to understand the nature of the shapes of these craters, because one of the things he was interested in, and he is interested in, is measuring the the angle of the crater walls, how steep are they? And there's one of the things that keeps coming up is like, well, one side seems to be a lot steeper than the other. And here's crater Stickney towards the north. If you measure it geometrically from the center of the crater down through the center of Phobos, you'll find that, okay, the north slope is approximately 37 degrees, whereas the southern slope is 23 degrees. But if you adjust this for the dynamics of the rotation of Phobos, the gravity of Mars, and so forth, it turns out that there's less of a pronounced difference. Down, if you hold a plumber's tape or a plumber's line, you'll discover that down really isn't down. It's offset a few degrees because of the dynamics. So your plumber's line is not going to point directly at the center of Phobos. It's going to be offset slightly. So when you're taking measurements as far as like angle of repose and the effects that slope will have, you can't just measure the geometry. You have to measure what is dynamically down, not what is geometrically down. So the next one is more of an extreme case of this. Crater 214, it's an unnamed crater. There are, I believe, 17 named craters on Phobos. And here's a pretty good sized crater. It looks like around 2 kilometers in diameter. It's in the southern hemisphere. And as far as the geometry, it appears that the northern part of the rim is tilted quite a bit higher than the southern tip of the rim. However, when you correct for the dynamics, the rotation of Phobos, the forces that are applied by gravity in that environment, the opposite is true. It turns out that if you're standing in the bottom of the crater, down is not where you think it is. Down is off by, it looks like maybe 14 degrees. So you imagine you're standing and you're holding your plumb line and you say, okay, I have this stick that's pointed straight into the center of Phobos, and you compare that to your plumber's line, it's going to be off by quite a bit. So this whole idea of understanding the gravitational dynamic where you are at the time is really important when you're trying to understand downslope movement and mobilization of material, because it may be that down isn't quite where you thought it was according to your geometric map. Okay, so looking at craters in general on Phobos, the chart on the left, I'll point to this. This is a size frequency distribution of craters larger than 2 kilometers on Phobos, and it follows a curve that is considered to be what we call the equilibrium distribution, which is essentially the point where if you add a new crater of a given size, it destroys just as many craters of that size as it replaces. So we have a term, we call it saturation, crater saturation, or whatever. But what it's saying, what this chart is saying, is that at least at these sizes, Phobos has reached saturation. If you were to add a new crater to Phobos, especially one of these larger craters, that it would not change the population of craters that are on Phobos. And that suggests that Phobos is a really old object. It's been somewhere in the solar system for a very long time. It's been exposed, the surface has been exposed to impacts for a very long time. This is not an object that recently broke away from something else. It's not an object that's had its entire surface completely renewed recently. It's an old body. Okay, now on the right side, it took me a while to kind of understand this, a little bit of back and forth. And when you look at the depth diameter and you compare that to the size of the craters, there is no relationship. There's the sense that if you have a big crater or a small crater, they come, some of them are old, some of them are new. Okay, well, maybe this is what you would expect from a very old body that's been exposed to a lot of impacts over a very long time. Some of those impacts are going to be younger, you're going to have a deeper depth diameter ratio, and some of them are going to be older and they're going to have a more shallow depth diameter. It's more evidence that Phobos it has been around for a long time. Okay, so this is a little bit of summary from about this. Where Sasha is saying that, okay, we have reached equilibrium, we've reached saturation on Phobos. And he's referring to Nico Schmiedemann, who presented this information in the bottom part of the slide in the second week. Nico is trying to understand, well, how old is Phobos, and then how old is Stickney Crater? And if you're working with craters that are greater than 2 kilometers in diameter, or maybe 1.5 kilometers in diameter, that will work because these are the big background impacts from the solar system. You're only going to get those kind of sizes. But craters smaller than that, as I talked about a few weeks ago, especially those that are less than like 1 kilometer in diameter, those are going to be mostly secondary impacts. So Nico's work here is excellent in characterizing the size-frequency distribution, but we have to be really careful when we get to looking at Phobos on smaller scales, smaller size craters, that it becomes increasingly unreliable because many of those craters are going to be secondary impacts from debris from ejecta that is trapped in orbit around Mars and returns to Phobos over time. Okay, and now even after taking into consideration the dynamic process of the gravity, the rotation of Phobos that alters the nature of what is down, Sasha was interested in some of what seems to be an odd characteristic of craters on Phobos. They don't seem to be terribly symmetrical. Okay, so the first chart on the left plots out the maximum crater wall slope versus its depth diameter. So if you compare that to lunar type craters, we're seeing slopes in general, at least at the maximum, that are steeper than we're seeing on the moon. Okay, well, there's less gravity on Phobos. Perhaps that makes sense because you could have a higher angle of repose. Now, the next thing that Sasha does is he says, okay, I'm going to compare that angle with the opposite side. And you would think, okay, well, maybe they'll average out. And it turns out even that is a little bit higher than on the moon. But nonetheless, what he's observing here is that you have one side of craters, the one wall on the craters of Phobos is going to be steeper than the opposite wall. It's not quite as symmetrical as you would expect on the moon. Okay, regolith on Phobos, as I talked about a few weeks ago, it's the consequence of a lot of re-impacts on Phobos from ejecta that's in orbit around Mars. You have a primary impact, almost all of that ejecta goes away. Some of the very slowest ejecta stays locally, and that's what we can see in these two images here. Most of it goes away, and you have a multi-stage repeating process of ejecta coming back to Phobos and producing more ejecta that gradually settles down as the energy is dissipated. So in a way, you could have a very fresh impact on Phobos, but over the course of 1,000 years, all of these secondary and tertiary impacts come back and rework the surface, and you could have a crater that's only 1,000 years old, but it can still look very old because of this reworking process. This is a very important slide because one of the questions you're going to ask is, well, how thick is the regolith on the surface of Phobos? And it's one of those questions everybody wants to know. If you dig down, how far do you have to dig down before you get past the regolith and into the solid part of Phobos that's down underneath? And Quaid and Overbeck performed experiments in the 1960s to work out how you can understand the regolith depth just by characteristics of how it's accumulating in the bottom of craters. So there are three different kinds of craters here. You have one where you have a sort of a flat bottom. You have another in B, which is you don't really see much of anything. And in C, you see a concentric ring. And those can be diagnostic tools to give you a sense for what is the thickness of the regolith compared to the diameter of the ring, just by looking at the character and nature of the craters. So you can calculate the regolith, if you know the diameter of the crater and you know what kind of morphology you're seeing in the floor of the crater, you can set limits on what the regolith thickness is. So this is a map, and once again I invite you to download the slides if you want to have a closer look at this. Looking at various craters that show evidence of these sorts of accumulation properties and annular properties and so forth, and we can see that there's quite a variety of calculated or estimated regular thicknesses, everywhere from almost 400 meters where I'm pointing here to other places that are a lot thinner. Clearly it's an estimate. Clearly it's probably accurate to within a factor of 2 or 3 or something like that, but it does give a working diagnostic tool to get a sense that, okay, well, we know that the regolith is not thin. We know that there's a lot of regolith there. Thomas et al. In 2000 estimated that the regolith, depending upon where you're looking on Phobos, ranges from 5 to 100 meters in thickness. And then, based on what I talked about a few weeks ago, the amount of regolith that's produced by Stickney, which would produce a lot of regolith, is somewhere in the neighborhood of 30, 40 meters of additional global equivalent. So we put all those pieces together. Okay, we have a source for where the regolith is, and it's pretty much comparable to what we'd expect. Shallower craters are likely to get rid of more regolith than they produce because they're not excavating through the regolith, or more preferentially launching a lot of that out into solar system orbits. So the regolith, the new regolith, is probably produced by bigger craters like Drunlo and Stickney and so forth that excavate underneath and get down and to launch out new material. Okay, I know there are other aspects of these craters. I mean, Phobos, you think, well, okay, you talk about a crater, you sort of think about this round shape, but a lot of craters on Phobos aren't round, and they could be due to oblique impacts, which we see in A. In B, this is Crater Hall, near the south pole of Phobos, and it's almost rectangular. It's a very strange shape. Now, on the Earth, for instance, Meteor Crater in Arizona, we'll see a sort of a squared out shape, and that's due to the underlying structure of the target, joints and fractures and faults that were already there that preferentially allowed the ejecta to leave in a non-round pattern. And so Sasha suggests that possibly we're looking at that near the south pole of Phobos, that we have this rectangular shape that's indicative perhaps of structural weakness and faulting and so forth. It could also be just the geometry is such that there's no material to produce that round shape. And if you hit like the corner of a box, you're not going to get a round crater. You're going to get a very strange shape. Now, Sasha was also looking for other aspects of craters, and there are some examples where we have a lobe of material that's preferentially deposited, as you can see in B. That B is on Phobos. A is an example on the Moon, and we also see a lot of these on Mars, which on Mars it would be indicative of subsurface water ice. But what Sasha is saying is be careful about that, because you can also apparently get that same sort of lobate morphology as we see in A on the Moon, which we don't expect, at least not near the equator, to have any sort of deposition of ice. But anyhow, we see a lot of different kind of craters on Phobos. Okay, now the whole area of boulders is something that Sasha is very interested in. We're all very interested in, because, well, they're material that potentially comes from the interior of Phobos, so we're interested in that. It's also they're diagnostic of age, because boulders do not survive on the surface of airless bodies indefinitely. They are destroyed over time by meteor impacts. So here's a slide I showed a few weeks ago. These are boulders on the Moon. You can see boulder tracks coming in from the right. And over time, these boulders are destroyed by meteor impacts. Now, as Sasha likes to say, some of them get lucky and some of them don't get lucky. And so if you have a population of boulders, they're not all degraded at the same rate. Some of them may be impacted. They just may get a big impact that the other ones didn't. So these two boulders that we see here may be of the same age, but eventually, given enough time, they'll be completely destroyed. Here's fresh ejecta from a crater on the moon, and the next slide will show a series of snippets of about 100 meters square on the moon, just to get an idea of what happens over time when we're looking at the moon. So if we go through A all the way through L, we're basically seeing a fresh ejecta from a crater that's maybe 2 million years old, and we go all the way down through the process, and we see fewer and fewer and fewer boulders that are left over from that survive the degradation process of meteor impacts. Now, at about 300 million years, let's see. Well, let's see. I have just lost my screen. Well, I haven't lost my. I'm seeing a blank screen. Anybody? Everybody's seeing a blank screen. Okay, it's back. It's back. All right. I'm going to count to 3. Give the computer a second to think. Okay, Ricky. Any ideas about that? Oh, got that one.
So right now I'm seeing, okay, that slide looks to be, yeah, I'm not sure if that slide came across properly.
Okay.
Is that the last slide of your presentation? No.
No. This is about halfway through.
Okay, yeah, looks like one slide didn't come through.
Let's go to the next one.
Okay, well, I'm going to keep going until I see a slide, but I'm not seeing any more.
Okay, stand by.
Okay, well, I'll keep talking. I've looked at these slides recently enough. Yeah, the next part of this, really, it's the question of how long do these boulders survive? And they survive up to about 300 million years. We still see a very small population after 300 million years on the moon. So the question is, okay, well, how do we translate that to Phobos? And Phobos, this is one of the things I spent part of last summer working on, is to try to get a sense for what's the flux on Phobos compared to the moon, just the total number of impacts, and the velocity of impacts. And based on that, it's possible to calculate the difference. And it turns out that on the leading hemisphere of Phobos, the flux, the impact flux, the energy that's available to destroy boulders is about twice as much as it is on the moon. So you would expect that on Phobos, at least on these 1 meter scale boulders that Sasha has been studying, that on Phobos, on the leading hemisphere, they'll be destroyed in probably 1 to 200 million years, something like that. And on the trailing hemisphere of Phobos, the flux is about the same as on the moon, so that would be 200 to 300 million years, something like that. And so the question is, we have a real big problem because we don't have images of Phobos that are down to 1 meter scale. We don't see them at all. So because of that, so we're seeing boulders that are maybe down to 3 or 4 meters, something like that. So how do we take what we know about the moon down to 1 meter scale, lasting maybe 300 million years, and compare that to Phobos when we don't have images to show us that? So one of the slides, hopefully we'll get back to, is we can see a curve of fall off that's due to resolution. But if we throw away the curve that's due to the fall off of resolution and apply that to the lunar scale, we can see that okay, it's following the same sort of curve. So the real question would be to ask then, okay, how long do boulders last that are 5 meters in diameter or 10 meters in diameter? And so there's an image that hopefully I'll be able to show you of the rim of Copernicus crater, where we don't see any boulders at all. They're gone. If there are boulders there, they're from fresh craters in the immediate vicinity, clearly associated with those craters. But the ejecta boulders that are associated with Copernicus are gone. And we've pretty reliable information that Copernicus crater is about 1 billion years old. And so if you interpolate what we're talking about, where Phobos on the leading hemisphere, where Stickney crater is located, has twice the impact flux, you cut that 1 billion in half. And that's where the estimate of the age of those boulders that are associated with Stickney comes from. It's 1/2 of the age of Copernicus that we normalize for the flux at Phobos. Okay. Still no luck?
Okay, hold standby. Here, I'm going to go ahead and share my screen, and then just tell me to advance the slide.
Okay.
Are you seeing it now?
I am not.
No,
No, there.
no, negative.
I am not, and the others are not.
Okay.
I've got slides, but you see.
No, Ricky can share them.
Yeah.
Or I could, well, whatever.
Are you seeing my desktop at all?
No, I am not. I'm seeing the same thing, and that's true for everybody here
Yeah.
on different computers. Okay, let's see, what else can I say?
Yeah.
Well, one of the things, let me do a little comparing to Deimos. I talked about how Phobos rises every 11 hours, is in the sky for just 3, and it's gone. So you can imagine you're trying to do teleoperations from Phobos, and okay, you've got a 3-hour window. That could probably be kind of handy. Now, Deimos, on the other hand, is out just beyond the geosynchronous altitude, the synchronous altitude, and it's slowly drifting behind the rotation rate of Mars. Now, Deimos will rise, I believe, about once every 5.5 days. It rises in the east, it obeys the rules, but it doesn't set right away. I mean, the day, night, it'll go about 2.5 days. It'll just be in the atmosphere, in the sky above the surface of Mars. So it will rise very slowly, continue to rise. So if you're doing teleoperations from the surface of, okay, I see your screen, Ricky. If you're doing teleoperations from Deimos back down onto Mars, you'll have a continuous 2.5 day window, and then you'll have to wait another 3 days before you come around again to that one spot above Phobos. Okay, excellent. Okay, Ricky. Can you? Yeah, that's good. Okay, so this is the slide I was talking about as far as the rate of destruction, and after just tens of millions of years, about 50% of the boulders on the moon are destroyed, and after about 200 to 300 million years, most of them, 99%, are destroyed. Okay, next slide. Great, and this is the chart I was talking about, where you have a fall off in the distribution of smaller boulders in the images that we have available, but that's due to the image degradation. If you ignore 2 and 3 meter diameter boulders in the images of Phobos, it pretty much follows the pattern that we see on the moon. Next slide. Okay, and this is the image I talked about as far as Copernicus, where we don't see ejecta boulders from Copernicus. And we know that Copernicus is about 1 billion years old. And so if we normalize that for the flux in the leading hemisphere of Phobos where Stickney is located, the fact that we see boulders there suggests that those boulders are less than half a billion years old. And considering that there's the Thomas et al. 2000 and others have related these boulders to Stickney Crater as ejecta boulders, that suggests that Stickney Crater is less than a half a billion years old. Next crater. Next slide, please. Okay, and this is a sort of a summary slide. It reiterates what I just said. But on the left, you can see kind of a strange map of boulders that have been mapped by Thomas, and that's limited just by the amount of resolution that we have. Next slide, please. Okay, so here's some different aspects of craters. We see a lot of downslope movement on crater rims and different craters on the surface of Phobos. Stickney is A, and there you can see landslides and mobilization. You can see material collecting in the floor. All of this is indicative that there are dynamic processes. Now, what might be driving that? You could imagine that if you have a major impact somewhere else on Phobos, perhaps it's seismic shaking that's producing this. Next slide, please. Okay, and here's another one, more of landslide material that A is collected in the floor of Stickney Crater. And there are analogs elsewhere in the solar system from Giordano Bruno on the Moon and Iapetus Crater. Next slide, please. Okay, so we've talked about the red and the blue units, and the blue unit really is a red unit that just isn't quite as red as the red unit. But when you make adjustments, you can pull it out. Next slide, please. So just trying to get a sense for the underlying material of Phobos. What's down under there? Well, we have natural probes called craters that dig down into this surface, and here along the rim of Stickney, we have two craters, both about 800 meters in diameter, very close to each other, within 1 or 2 kilometers of each other, and one of them it is showing red ejecta that's preferentially heading downhill away from Stickney according to the dynamic gravity rules in that vicinity. And right next door you have one that's mostly blue ejecta. There's a little bit of red there. And you'd have to ask yourself, well, if you're excavating material, could you have such different units that close to each other? And of course, you could also speculate that we're not looking at the units. Maybe we're looking at lower velocity secondary impacts, and one of the blocks came from a red unit and one of the impact blocks came from a mostly blue unit, and so the streaking that we see by the red crater could be just the nature of the impactor that produced it. Next slide, please. So this is a map from Sasha where he's pointing out these differences. They're on the rim of Stickney within the blue unit. Most of the craters, but not all, seem to be excavating blue material or depositing blue material or interacting with blue material, whereas other are excavating or depositing red material. So it's a bit of a conundrum, but to have such a dichotomy of units and evidence so closely intertwined. Next slide, please. Okay, so this is Sasha's model, or a couple of models. I believe he even has more than these. But the idea is that perhaps you have regolith and you have deposit of red material. This is case one of red material on top of blue, and you get an impact into that, and you'll have deposits which is a mixture of each. And in the case two, perhaps the crater goes into mostly one kind of unit, but near the rim of the crater there are other units. And so this suggests that maybe Phobos is a conglomeration of very different blocks of material. Next slide, please. So this is one potential model that could be used to work this out, that maybe right next door you could have an impact into a blue unit and right into a red unit, and you'll get red ejecta and blue ejecta. And so Okay, Sasha is saying we're going to need to do more investigation to understand this. Next slide, please. Okay, so one of the questions is, this has come up before, is how much ejecta from Mars ends up on Phobos and Deimos, and Chapaz et al. Worked out a very low amount for Phobos and even less for Deimos, and Jim Head and I worked on this just about the same time and drew essentially the same conclusion. And it turns out, one of the questions we want to ask is if you see boulders on Phobos, do you really think that this is from Phobos and packages it up into boulders? You get 10 boulders that are diameter of 40 meters in diameter. So it's really not enough material such that if you found a big boulder on the surface of Phobos that you could say it came from Mars, because we're talking about 500 million years of deposition. And also keep in mind that ejecta that comes from Mars and intersects Phobos is going to collide with Phobos at velocities typically 2 to 3 kilometers per second. It can be a little bit slower, but that would tend to break up larger boulders too. So one of the ideas is if you go to a good-sized boulder on the surface of Phobos, there's a really good chance that material is low-velocity ejecta that was excavated from depth at Phobos. Okay, next slide, please. Next slide. Sasha investigated grooves and characterized them, and they're very shallow, and they're very subject to the lighting conditions. So if you're looking for grooves and you're trying to study grooves, it's important to try to get as much data as you can from different lighting conditions to really get a sense for how many there are and where they're located. And John Murray also points that out, that if you had adequate lighting conditions for the surface of Phobos, you would see a lot of grooves there. Next slide, please. Okay, and one of the things, this is Sasha's hypothesis for grooves, that they're tectonic features, that these are joints or faults. The grooves demarcate those, but he also observes that there's no evidence of lateral displacement that you might typically see if this were a collection of blocks and joints that are all lined up. Eventually, at some point, some process, some local large impact, something would likely displace that. So he's not abandoning the idea, but he is pointing out that the sort of evidence that you would expect from joints isn't, at least to this extent, has not been observed. Next slide, please. And as John Murray pointed out, and I believe I pointed out, that these grooves, some of them nearly wrap halfway around the one hemisphere of Phobos. They are extensive, and they're linear, they're continuous. And so there's a lot of things here that once you start describing the grooves, you begin to realize how you're setting constraints on the processes that are necessary to produce them. Next slide, please. Okay, and to compare and understand different processes, Sasha is looking at the hypothesis of rolling boulders as the source of grooves, and perhaps Stickney Crater or other craters produce boulders, large boulders, and due to the dynamics of the Phobos system and the gravity of Mars and so forth, that these were propelled and continue to move in motion around the circumference of Phobos. And so to compare that, well, we're looking at boulders on the surface of the moon, and especially in D, Sasha is pointing out how when a boulder is rolling and crossing a crater, it tends not to just be a smooth, continuous groove. It tends to break up. The distance that the boulders are bouncing between local recollisions with the surface vary. So, he says, well, maybe that you should expect that on Phobos, in which on Phobos we see lines that are straight on through, almost no deviation at all. So, okay, there's some difference there and something to look at. Next slide, please. Okay, and then looking at grooves elsewhere in the solar system. This is on Eros, and we do see grooves on Phobos, on Eros that look a lot like Phobos. especially in A. I mean, if you showed me that image A and said that was from Phobos, I would say, well, that's probably the sort of thing you might see in the southern hemisphere of Phobos, where the grooves are a little bit more spread out. Okay, next slide, please. And this is asteroid Letitia, and Letitia is nowhere near any other planet, so you don't really have you don't have tectonic tidal forces, and you don't have a source for secondary impacts. But nonetheless, we're seeing grooves, features, chains of pits, or whatever, however you want to describe it, that look very similar to what we see on Phobos. Next slide, please. And then we have troughs on Vesta, which are really, it's really unfair to compare them, because you could take the entire body of Phobos and lay it in that trough. The trough is considerably wider than the Mississippi River. So, but we do comparative morphological studies, and this is clearly an N member. There are other hypotheses that work out where these troughs may have come from, and I will leave that to others who are expert invested to talk about that. Next slide, please. And then, okay, this is on Elysium Planitia on Mars, and we're seeing joints and fractures and okay, so these, if you're imagining that grooves are maybe regolith material that's falling in between cracks, well, these would be perhaps the sort of cracks you might see, although these are not quite as well organized as you see on Phobos, and they show evidence of displacement that we don't see on Phobos. Next slide, please. Okay, so here's Sasha's summary of potential sources for the grooves: fracturing and faulting, and bouncing boulders, rolling boulders, and chains of craters from impacts on Mars. And these have all been discussed and talked about quite a bit, and I won't take it any further. Let's go on to the next slide, please. Thanks. Okay, back to our map, and once again I invite you to have a look at this map at your convenience. Clearly there's a lot going on the surface of Phobos, and when we're there, a lot of these craters will offer opportunities to explore what's down deep underneath the regolith. Next slide, please. Okay, Deimos. Deimos, I already talked a little bit about this, how it's different than Phobos. One of the things that's clearly obviously different is that it doesn't appear to have any grooves. It's the surface area of Phobos is about 1/2 that of Rhode Island, so we can be happy here in Rhode Island that we found an object in the solar system that's smaller than the landmass of Rhode Island. I'm from Massachusetts, so I really have to be careful when I say these things, but and as I pointed out, it's even though it's okay, it's at a higher orbit than Phobos, it still has a strange orbit. It rises once every 5.5 days, hangs around for 2.5 days in the sky, and then disappears, and then rises again 5.5 days, almost irrespective of the day-night cycle of Mars. So it's not like our own moon, where it rises about 12 degrees different than the day before. The moons of Mars are rising and setting pretty much on their own schedule. It's dark like Phobos. It has even lower density than Phobos, and escape velocity is very low, although it doesn't have so many of the dynamic problems of Phobos, where Deimos is far enough away from Mars that you don't have to worry about going left and right as to which way you need to go to stay on the surface. Next slide, please. Okay, and the map. This is a map of Deimos. Certainly a lot more to learn about the different details of Deimos. Next slide, please. And this is actually some images that Dan Britt showed during the first class, and you study this and you find boulders on the surface of Deimos. You also find a characteristically odd distribution of craters that are they seem to almost be slowly being buried by a continuous infalling of some material that gradually is burying older craters, and whereas you see fresher craters that are placed into this. And as Dan pointed out, which is really one of those odd sort of things, is this may require looking at the slides, downloading the slides, but if you look at these craters, they all seem to have a preferential downwind distribution of material that's coming off the rims. And it's like, well, okay, if this were on the surface of Mars or someplace that actually had an atmosphere, that might make sense. But what sort of process would preferentially distribute whatever this material is that's collecting on the surface of Mars? What would preferentially push it all in this direction? That's a mystery, and that would be something that would be worth some additional thought. Next slide, please. Okay, concluding remarks. Next slide, please. We see a variety of craters on the surface of Phobos. They're generally similar to craters on the Moon, although they tend to have unusual outlines, largely perhaps because of the irregular shape of Phobos and the irregular dynamic properties of Phobos. The regolith of Phobos is, for the most part, a product of impacts that produce ejecta that sends most of this ejecta into orbits around Mars, and that returns over time. The steepness, even though there's very little gravity on Phobos, the steepness of fresher craters in particular appears to be enough to mobilize material. And of course, we've talked about the grooves, and even after we've done a sample return mission, I have my doubts that we will have resolved the nature of the grooves. We may figure out where Phobos came from and how old it is and what it's made out of, but the grooves are going to be a continuing mystery, in my humble opinion. Okay. And also there should be some material from Mars. There will be some material from Mars, but it will be in the hundreds of ppm kind of concentrations. And it will be interesting to try to sort that out from samples. It depends on how much Phobos looks like Mars will allow us to sample Mars. Or if Phobos looks a lot like Mars, we may not be able to ferret out what is Mars and what is Phobos. Okay, next slide, which is last slide, essentially. In Deimos, it's geologically similar to Phobos except for the grooves, which Sasha is suspecting may be due to lower tidal stress. And Sasha also wants everybody to know that the Russian space program in the early 20s will be sending another mission to Phobos and to collect material. It's called Boomerang. And I would suggest that you investigate this further to find out how they plan to bring material back to Earth. And then Phobos and perhaps Deimos are candidates for further exploration in various ways. So thank you for your attention and your patience. And with that, we will move on to the question and answer period.
Well, thank you very much. We have a list of questions, and we'll get through as many of them as we can. First, some general ones, going back to your crater discussion. You had mentioned that all of the craters are essentially simple craters. One question relative to that was, is there impact melt seen in any of these craters?
I'm not aware of that, but that's not to say that it isn't there.
Maybe it's a resolution.
It could be a resolution. You might see it spectrally, but we don't. A lot of the craters have deposits of regolith, so even if you have a half a meter of regolith deposit over top whatever melt is there, we may not see it. I would suspect, given the velocities that are possible in impact at Phobos, there should be impact melt. We just don't see it.
Okay, a second general one was, you had mentioned that both Phobos and Deimos have the same face to Mars. So are there any differences in the far side of Phobos compared to the near side, such as we see on our moon?
Interestingly, no. And that's kind of, that's one of the things I was looking at when I was studying the trajectories of ejecta from the surface of Mars up to Phobos. And, especially the hypothesis that the grooves may be crater chains from impacts on Mars. And it turns out that in order to produce those crater chains on the far side of Phobos, the ejecta has to fly out past beyond the orbit of Phobos and come around and hit Phobos on the way in. So, if you think about that, the crater chains that are emplaced on the near side of Phobos are orbits or flight times of maybe 20 minutes or a half an hour, but the crater chains that would be in place on the far side of Phobos would require up to 1 or 2 hours in order to reach that destination. So if you would expect a difference on the near side versus the far side in the character of the grooves, because just the flight time alone would spread out the impactors and dissipate them into a less organized pattern. But as a matter of fact, when you compare the grooves on the near side of Phobos to the far side, the pattern is essentially indistinguishable. And that's generally true for craters and regolith depth. And we don't have uniform imaging to pin down the very finer details. And spectrally, there are differences. We have it's more blue in the vicinity of Stickney to the east of Stickney. So there are some regional differences, but in general, Phobos is fairly the same anywhere you look at it.
Okay, there's a couple of questions concerning impact flux and some pretty fundamental issues. First one perhaps is more appropriate for Nico, but let me pass it on to you, see if you can answer it. This is from the UCF. Would the re-impact flux from Mars or Phobos ejecta mimic the effect of crater age and make Phobos appear older than actually if it were just non-Mars flux that's in the cratering frequencies? Sure.
No, that's a good question. As Sasha points out, and it's a matter of his research. It looks definitely like the surface is saturated and consistent with an ancient age, and that goes all the way up to the larger craters. Now, as far as secondary impacts, the largest secondary impacts are going to come from Stickney crater, probably. And according to our modeling and error bars and everything else, the largest sizes you're going to see, and there won't be that many, will be in the neighborhood of maybe 2 kilometers in diameter, and that's kind of pushing it, maybe 1 kilometer diameter. So it would in smaller sizes. If you're counting craters in smaller sizes, 1 kilometer or less, it's going to look old. There's no doubt about it. It will definitely look old because of how many secondary impacts you're getting from Stickney and from Drunlow and from all of these other big craters. But when you look at the larger craters, the 4 kilometer craters, the 3 kilometers, the 5 kilometer craters, and you do a size frequency distribution of that, and those are too big to be secondary impacts. So that's indicative of the age of Phobos, and that suggests a very old age.
There was another question that I think you just answered about, maybe you mentioned that there was a cutoff of secondaries at 1 kilometer. I think that gets convolved with what you were just talking about. So let's jump over that, and if that needs clarification, people can restate it in the questions. Moving on. Is the reworking of ejecta on Phobos a major contributor to the generally featureless spectra, or is this more a function of the composition of the body?
I should probably leave this camera pointed at Carl because I can speculate, and maybe you would want to comment on that, Carl. Yeah.
Well, actually, that's a very, very good question, and we will be discussing the regolith and space weathering issues in a few weeks. There is no simple answer to it, but we will discuss it more. So I will do what Dan did, namely forward the question to future sessions. Okay. Question from Stephanie. Would we expect the re-impact flux from Mars on Deimos to be much smaller than that for Phobos due to Deimos further out in the orbit? On how do the crater counting ages compare for Phobos and Deimos? And could anything be said about their mutual formations from this information?
Okay.
In other words, are there differences or not, and how does that affect their origin?
Yeah, well, I'll try to step through that. Well, the first thing, in general, the observation is correct. It's further from Mars, so the processes are going to be somewhat different. So I'll talk about a scenario where Deimos has a fairly large impact. It will have the same general process that's been described as far as Phobos material. A portion of the material will be trapped in orbit around Mars, but because it's not so deeply embedded in the gravity well of Mars, a higher proportion will escape to solar orbits. I haven't done the modeling for that, but just from the orbital velocity, which is about 70% that of Phobos, and the distance from Mars, it could well be that twice as much. Phobos loses maybe a third of its ejecta to solar orbits, or to the surface of Mars. Deimos probably wouldn't lose much to the surface of Mars. It might lose more than half to solar orbits, but you'd still have that process of material returning to Deimos from an impact on Deimos. Now, with respect to trying to understand how that relates to the origin of Phobos and Deimos, I really don't know. Deimos is definitely experiencing a different geological process because the surface character is different. Whether or not that suggests a different origin or simply a common origin with a different process that's been ongoing since its origin, that's a question I don't think we're able to answer right now.
If the underlying character Phobos is a rubble pile, how would that affect crater shape? Is there anything predictable in that?
Well, Sasha was speculating that if you do have a rubble pile, you're going to have joints and faults and fractures and so forth, and that will preferentially weaken the subsurface in various ways, and if you impact into that, you'll get a non-round crater. That very well may be true, and there's no reason to think that Phobos is not a rubble pile. There's no evidence to say that it isn't. But Phobos is also a very irregularly shaped object, and as I pointed out, if you have a crater on the corner of a box or on a very unregular surface, you're probably not going to produce a round crater in that instance either. So the fact that we have irregularly shaped craters helps support the idea of a rubble pile, but there are other reasons why you're going to have irregularly shaped craters.
Okay. There's some curious about these craters that indicate or have crater lobes, possibly suggesting water ice, if you take the Mars analogy. Are those common, or was that just an unusual example?
That's an unusual example. I don't know how unusual, but in Sasha's slide he says in rare instances or something like that. And it was really more of a cautionary slide, which is to say that just because it looks like a feature that's associated with water ice on Mars, and you get that sort of lobate shape on Mars, that you can't necessarily say that indicates water, but it doesn't rule it out either. But Sasha is saying you can get that same sort of morphology on the surface of the moon, where we have little reason to believe that there's a lot of water ice sitting there.
Here's another pretty fundamental question concerning the boulder degradation time. And Stephanie asks, how can the boulder degradation time on Phobos be directly compared to that on the lunar?
That's a good question, and there are several subtexts to it. Well, the direct comparison is that and unfortunately, this is right about where we were having problems with slides, so I wasn't able to explain it as clearly as I wanted to. But on the moon, we have a sense for the average impact velocity of projectiles that intersect the moon. And from modeling, we also have a sense for what that flux rate is. What we do is we just call that a unit of 1. The moon equals 1. And so now we look at Phobos and we work out for the leading and trailing hemisphere of Phobos what the average impact velocity is for Phobos. And then we model the distribution of all of the asteroids in the solar system. That's what I was doing last summer. I had a model where I included every single known asteroid in the solar system in order to work out the proportion of flux in the vicinity of the Earth versus the proportion of flux that you're going to have in the Martian, the vicinity of Mars, and then I worked in the orbital velocity of Phobos, a lot of parameters. But what we do is we say, okay, the energy of an impact, a typical impact, average impact on the moon is 1. What's the energy that's delivered to the surface of Phobos? And it turns out you have lower velocity at Phobos, but the flux is close to about almost 4 times as much, 3.5 times as much. So when you compare those, the total energy that's being delivered per unit, per square meter on the surface of Phobos is about twice as much as the moon for the leading hemisphere of Phobos, and about the same as the moon on the trailing hemisphere of Phobos. And okay, so then there's a subtext to that, which is what happens. You know, you run into a boulder, does that just break the boulder and that's all that happens, or are there secondary processes? And there's considerable discussion about secondary processes like thermal cycling and so forth. If you have thermal cycling where the rocks are expanding and contracting on lunar day-night cycles versus Phobos day-night cycles, how does that change things? Are there grain levels thermal cycling that's breaking it up? So the subtext is, we can compare the dynamic process of impacts, but there may be other processes going on that are somewhat different between Phobos and the moon, and we're aware of that. And so it's not exactly an apples and oranges, not an apples to apples comparison.
Okay, going back to the grooves, and there's 2 questions that came in from 2 different places that really focused on the same thing. They're concerned about the model of how can small amount of ejecta from Mars interact with the idea that the grooves are created by ejecta streams. In particular, it's a mass balance issue that people are concerned about. Do you have any comments on that?
Yeah, I haven't actually come right out and said it before, but yeah, it is a problem, and it's we studied that in great detail, and the mass balance is way off. It's close to, it's more than 3 orders of magnitude insufficient in terms of the amount of ejecta that both Jim and I predict and Chapaz et al. Predict coming from Mars and intersecting Phobos. That amount of ejecta is insufficient by at least 3 orders of magnitude in order to produce the secondary impacts that are modeled as chains that,
Could that vary with time?
What we're looking at is over the last 500 million years, we have a total volume of ejecta from Mars that intersecting Phobos that's equivalent to 10 boulders about 40 meters in diameter. So that's enough maybe for 10 pits. Of all of those pits that you see, I think I'm up to about 250,000 pits that are required to make the grooves as secondary impacts. So we can account for about 10 of them as from the ejecta, or I'll be charitable, maybe 40 of them from ejecta from Mars. But it's woefully insufficient to account to produce grooves as secondary impacts.
Oh, as you can expect, we do have a number of questions concerning Deimos, and one question concerns the wind streaks on Deimos. Could they have any relationship to the odd dunes seen in Comet 67P.
Yeah, we're not going to try to pronounce that. Yeah. Okay. I I would doubt. I would doubt that we're in a position to even speculate. Let me put it that way.
Probably a good answer.
Yeah, I mean, I have my working hypothesis for the wind streaks on Deimos. I have yet to test that or even develop enough of a model to say that I want to even say what my hypothesis is. But you know, comet dunes. I mean, probably on a very, very, very basic level, there could be somewhat similar processes. But and one of the things we learn in geology is that something that looks the same, you know, it has really two options. One is that it has a similar process, and the other is it doesn't. So we're kind of, we need more information.
One more question on Deimos, then there was a couple of questions that I skipped over. Roberto Campins asks, is there an estimate of the regolith depth on Deimos?
I'm not aware of it, but that's not to say that somebody hasn't done that. You can sort of get a sense because you can look at the craters that are slowly being buried, or I say slowly being buried. I have the sense that they're slowly being buried. And you know, if you look at what looks like a fairly fresh crater, and it's 100 meters in diameter, and it's mostly buried with what looks like these deposits, these wind streak deposits, or whatever that material is. And if you assume a simple crater depth diameter ratio of 5:1, okay, well now you're looking at regolith depth of 20 meters. So it's, you know, you can sort of do real-time science and work it out that way. But the other way to do it is if we can find some of these craters that have odd annular floor features and collections of flat deposits or whatever, that might give us some indications. But it appears to be quite a bit. You know, it certainly in the tens of meters would be reasonable, and maybe even more.
Given the crater population that you have on Phobos, for example, what portion of these craters show these evidence for landslide deposits or movement of material around Phobos?
I don't know the exact answer to that, but there is that map that's part of the slide package. That some of those are mapped. It's fairly common that you see at least some downslope movement on all fresh craters, anything that has a fairly steep wall. You see, you know, that's just from my experience looking at the images. There aren't that many images of Phobos. If you spend an afternoon digging up all the, you know, good quality Phobos images that are out there, you could almost answer that question for yourself. In fact, I invite everybody, because we've only collected, I don't know, maybe 80 really halfway decent, nice images of Phobos from different angles. And so this is not like looking at images from Mars where you could spend a lifetime just, you know, finding where they are, much less looking at them all. You could somewhat answer that question on your own and do some investigation that would really be helpful.
There is some interest in seismic shaking, and here's a question that you probably are prepared to answer. What scale of features can survive a resurfacing event like the Stickney impact? Obviously some did.
Well, yeah, I mean, it's sort of called the existence theorem. I mean, we see muted well, it's kind of interesting when you look at Phobos. If you're doing a brief geological description of Phobos, it's sort of like, okay, well, you have Phobos, this irregular shape. You have a lot of old muted craters. You have a lot of smaller, fresh craters, and then you have Stickney. So you have, you know, which is sort of both shares aspects of old and new morphologies. So you can imagine that perhaps Stickney, you know, okay, I'm saying it's a 500 million years old, ran into Phobos, tidally shook everything that's there, and everything, you know, in the neighborhood of 3 to 4 or 5 kilometers in diameter and greater survived that, and most everything else got shaken out. And then later you have secondary impacts and background impacts that backfill that. So you have an odd distribution. But I'm clearly, there are features that are surviving. It's just that they're, except for Stickney, most of the craters are somewhat muted.
Well, our time is running out. We've been at this for an hour and a half now, and I really want to thank you, Ken, for sitting in for Sasha, and for Sasha for preparing such an excellent and informative presentation. I want to thank all the participants for their questions, and I apologize if I didn't get to your favorite one. I think we touched on most of the highlights of the queries that people had. I want to thank our colleagues both at Brown and at the other classes that are underway across the country. Thanks certainly to Survey Central for providing support for this class, and especially to Ricky Guest for his technical support in getting us out of holes in the middle of our talk. Next week, we have a presentation by Dr. Joe Burns of Cornell, who will be talking of one of 2 lectures on the origin of Phobos, and his emphasis will be on the origin of Phobos, the dynamical evolution, and your moderator and host will be Dan Britt. For those of you who would like to follow up on the presentation today, it should be online shortly. I urge you to go to the website and look at the entire schedule as well as some of the previous lectures. Certainly all the reading material is there for your enjoyment as well. Thank you all for joining us. We hope that you'll be able to be with us again next week, same place, same time. Well, actually not the same place, it'll be all over. And as we adjourn for the day, I want to again thank you, Ken and Sasha, for today's presentation.